that are in the IECC and whole surface or continuous installation R values. This chart puts them in order of advertised R value. However, when you're talking about actual performance, this is actually the proper sequence. So the cheapest panel we make, a 4.5-inch EPS SIP, still outperforms code minimum in everywhere from climate zone 5 and up. And I didn't get a chance to ask where everybody is, but some of you may be in Tucson for all I know, in which case cooling is your only concern. But many of us have to deal with heat as well. Last week we had my thermometer outside registered 16 below. And I live, just so you know, our company's in New Hampshire, and then I live on the civilized side of the Connecticut River in Vermont.
Most everybody here is from the Northeast except for Carol, who's from Texas, right? There we go.
Okay, so all that stuff I said about conductive performance, Carol, you can ignore because your temperature differential across the wall or roof is relatively small. Because, you know, if it's 75 inside and 100 outside, that's only 25 degrees, not 70 or 80 degrees like we had last week here. Or even today when it's warm, it's 15 right now, and I've still got a 60 degree or 50 to 55 degree temperature differential. So the other place, and this is what will help Carol to a certain extent, is air infiltration. Depending on the building, especially in residential, a third, always at least a quarter, and sometimes a half, especially in older buildings, of the total energy consumption is driven by air leakage. And our default details, before we even get into the fancier stuff, is at or near passive house levels of air infiltration by default. If they do a blower door test and you're not totally blowing away anything that's quote unquote normal, you forgot to close the basement door or something. You can do SIFs badly, but when done with some amount of care, the air infiltration performance is really quite good because we're basically making a giant styrofoam cooler. You can get similar levels of performance with other systems, although, again, our market is driven by not by what's cheapest to stand up. That's not where we get a lot of jobs, but what is the cheapest thing to build and operate over the next 10, 15, 20 years. And then we become pretty wicked competitive.
Paul, I have a question. It looked like the first slide looked like you illustrated the construction. Could you go over how are the SIPs constructed? What are the different materials? It wasn't clear.
Okay, that is coming up. I'll accelerate a bit. Sorry, no problem. The purpose of this slide is just to illustrate that you can get similar levels of performance with other materials, and there is no one perfect material for every project. However, in northern climates, to get to our default level of performance, you have to do quite a lot of work. And that's where that's where energy versus construction cost balance is where our performance strength really is. The other thing that goes really well is construction is pretty easy. I said we do design work in our office, and that is, we don't commit architecture in our office, but we do panel design and structural design and a lot of building science design, or building science support for everybody. But we're building, you know, everything is pre-cut in our shop. We're sending a giant Lego kit to the site. Even with a rookie crew installing pre-cut panels, a normal 2,000 square foot house is a week-ish. If it's gnarly and got 43 roof surfaces, it'll be more. If it's our crew doing something normal-ish or conventional geometry-ish, 2, 3, 4 days, depending on the size of the job. The job on the left is the large commercial job, steel frame building that we enclose. And then the job on the right is an architect's house. Surprise, surprise, judging by its geometry. At least on this one, the walls were all plumb to each other, which isn't, or all plumb and generally square to each other, which doesn't always happen. But yeah, we were on site 6 days for a house the GC was figuring would be a few weeks to frame and then installation. So there are no studs. The panel itself is wood skins, OSB, and a foam core. And then honestly, it works exactly the same way as an I-beam. It's just, instead of having less material in the middle where it doesn't help as much, we have a weaker material in the middle that is also our envelope, thermal envelope, air barrier, an air barrier that hold everything together. Every material's got its structural limits. That's only a problem if you don't know what they are. And we've worked very hard to characterize our materials. When we've got a wall where you've got a truss or a roof system bearing on top of it, the OSB is carrying all the weight through the grain of the OSB, which isn't that strong until you prevent it from buckling. And having the two skins braced off of each other gives us really quite good buckling resistance. And I use the picture on the right because those very, very tall telecom antennas don't have half enough structure to stand up by themselves, but they always have not only guy wires going to the top, but 3 or 4 sets of guy wires stabilizing the middle of the column to prevent it from buckling. And that's exactly what we're doing with the skins of OSB of the panels. We do use dominantly OSB. We can do plywood, but only if you want expensive, not that flat, small panels. They aren't that strong. OSB gets a bad rap mainly because the salespeople oversold it. It absorbs water about as fast as plywood does, but it doesn't get rid of it half as fast. It's half as permeable. And the sales guys never mentioned that, so there's been a lot of bad rap given to OSB. And as with anything else, when you don't understand a material is when you're most likely to run into long-term trouble. There we go. So part of the reason we use OSB is that we can get it in giant sheets up to 8 foot by 24 feet. And to give you an idea of scale, we bring in 3 or 4 semis of 8 by 24 OSB a month and a rail car and a half of 4 by 24 OSB a month, which is a lot of material. We do about 240, 250 projects a year. Some projects are little sunrooms, some projects are high schools. So we make 4 different core materials. The skins are dominantly OSB, but the core is, we have a choice of 4. We can make all of them in a variety of thicknesses. All of them are such low permeance that it doesn't matter. And it comes down to a cost, a choice between thermal performance, structural performance, and cost. EPS, the white beaded styrofoam, is 60% of our volume because basically it's got the highest R value per dollar. It happens to have the lowest R value per inch, but if you can tolerate the thickness, if you let us make 2-foot thick panels, the R value is pretty stupid. We've sold 17-inch panels, but from an economic standpoint, they don't make that much sense on this side of the Arctic Circle. From a long-term carbon emission standpoint, embodied energy versus fuel consumption over time, depends on what your fuel source is, but most of our walls are 6.5, 8.25 kind of range. Most of the roofs people buy are 10.25, 12.25, 12 7/8 sort of range. That's really normal for EPS. Neopor is the gray foam, if you've ever seen that around. BASF's been marketing the hell out of it for a couple of years. Perfectly good material, higher R value per inch. We can hit your thermal goals with a thinner panel if that's an architectural need. But it's a bit more expensive, which is why it's not half the volume that EPS is. XPS is the extruded.
Paul?
Yeah, go ahead.
What would be for, you said you had a small house, I think you said 1,280 square feet, something like that.
Yep.
If that were a passive house, what would be the typical wall and roof thicknesses for a passive house?
Depending on your glass fraction, 8.25 or 10.25 inch walls.
Mm-hmm.
I've got 6.5 in the second floor here, and I've got 10.25 on the first floor for architectural reasons. And for passive house, we're doing 12 7/8 or 15-inch roofs, and mine happens to be 12.25. Within our normal schedule of materials, passive house level performance is, honestly, from my standpoint, it's just kind of a checkbox on the work order. There's much more work to be done in glass fraction, fenestration specification, and architectural design. You tell us what we need to be, and it's not a big thing. Is that a reasonable answer?
Thank you.
So, Paul, yeah, that picture actually inspired me for this question. Where is the, like you were saying, if you go to, after a certain thickness, it does get to be costly. You're actually not saving as much as you're actually paying. But where is the better, the more appropriate thickness where cost and R value actually are at a good balance?
If you're looking at it economically, where everything matters, but the primary decisions are being made on fuel cost, not CO2 emissions. In the parts of New England where everybody lives, Massachusetts, Connecticut, coast of Maine, southeast New Hampshire, 6.5-inch walls, 10.25 roof-ish. As you go south, everything kind of thins out a little bit. You have to go pretty far north to justify 10.25-inch wall panels on a strictly economic basis. I'll bet you half or 60% of all the walls we make are 6.5 EPS. It's at a really good place, price versus performance. We're blowing away energy code minimums. And you can still use pretty conventional materials when it comes to jam extensions and doors and trim and that sort of thing.
Just one other question. With these tests that you've been making with the 6.5s, have you noticed the type of window that they're carrying? Because the window does make a difference.
Not only does it make a difference, it dominates the equation. If you're doing a heat loss calculation, the conductive loss through the opaque wall is single-digit percents, maybe 10, 12% of the total heat loss. I can't tell you, we get phone calls every day from designers and homeowners and builders. Hey, what do you guys have for an R40 wall? And I'm like, unless you're importing your windows from Switzerland, there are much better ways to spend your money. I'll bet you 95% of the jobs we do, when looking at, you've got finite allowable construction costs. You got a limited budget, and for this budget, you're trying to make the highest performance building you can. It has been over a year since I've seen a design where the architecture and the specification of the other materials and the rest of the design warranted going past an 8¼ inch EPS wall.
Okay.
It is that rare. And those buildings are buildings that have very high specification windows and doors.
Mm-hmm.
Not that many of them that aren't that big. And they've already done the ERV ventilation system. They've already done the hydronic heat. They've already done 4 or 6 inches of insulation underneath the slab and 4 or 6 inches of insulation around the foundation.
Right.
Until you get there, stick to the modest panel thicknesses, because we'll happily sell you the more expensive panels, but I don't feel like I'm doing a good job for you professionally.
Okay. Cool.
So we've got Neopor, we got EPS, white styrofoam, Neopor, gray styrofoam, XPS, which this picture is old, so it's pink. Now it's blue because we buy it from Dow and not Owens Corning. XPS is only a few % of our production, because while its R value is very nice, it is very expensive and is, because the market, the North American market allows it, a pretty large environmental impact. So to be honest, the only time we use it is when I need its superior strength. And then the third material is polyisocyanurate, which is a cousin of the same rigid polyiso that is on top of the roof of most every big box store you've ever been at. Polyiso's got the highest R value per inch. It is also the one with the R value that people lie about the most. And it also is the weakest panel, but when you've got modest loads or relatively short spans, it works beautifully. And then the third material that we use that nobody ever sees except me and the production guys is the moisture cure polyurethane that we use to glue everything together. Fundamentally, it's 100% solids polyurethane. When it's cured, it's roller blade wheels. While it's curing, it emits gas, which is CO2. If you've ever used Gorilla Glue from the hardware store, this is an industrial cousin. The chemistry is fundamentally the same. And it is also the strongest component in the whole assembly. We've never had a glue failure ever of any kind. So, trying to anticipate the most common questions. What about outgassing? What about these crazy engineered lumber things? Yes, all sets outgas because they're made of wood. The EPA can't tell the difference between a piece of OSB and a piece of aspen that is sawn out of a tree, because the outgassing is coming from the wood fiber itself, not any of the adhesives. Many, many, many years ago, they used urea formaldehyde adhesives to hold OSB together, but that ended 15 years ago. The last of it died out 15 years ago. And the materials that we're using now, while I wouldn't eat a big bowl of them uncured for breakfast every morning, once they're cured into the OSB, they're really stable, and all of the outgassing and even emissions from combustion, it's dominated by wood. And just so you know, with OSB and plywood are similar in that they're about 4% glue by weight. It's 96% wood. The reason OSB looks as dense as it is not because of all the glue. It's because the 7/16 OSB that we make panels out of was about 3.5, 4 inches thick when it went into the press. And they're smashing all the void space out of the wood fiber. That's where the density comes from. So, residential, what everybody else is doing. It is rare that the building structure is only SIPs. You can see on the picture on the left that while the primary structure is SIPs, you can also see a glulam, ridge beam, and purlins holding the roof up. We don't do very many SIP floors unless we're doing a, I don't know, bedroom over top of a garage, where we're doing over top of unheated space. When you're separating heated space from heated space, the SIPs are a very expensive choice for not a lot of benefit. We do a lot of timber frame buildings, we do a lot of steel frame buildings, and we do a lot of load-bearing panels. For example, that commercial building I showed a few slides ago, They had a wing that came out the side of the building, basically a lower shed roof. And that's, in this right-hand picture is the inside of that. The steel bar joists that are bearing on a steel structure on the uphill side, and on the downhill side, they're bearing on the wall panels alone. And then we spaced the bar joists as far apart as we could within the limits of snow load and what the panels could do. So we optimized material use best we could. This is the assembly of that structural panel house that we showed. The beam in the middle, the purlin, using the timber frame terminology, we only need when the when the building starts getting wide and we start getting to high snow loads. In Carol's neighborhood, you have no snow, so we can span really quite far from ridge to eave. One thing we do, and this is a little, SIPs are good at this in general, but Ford Panel does it quite a lot. One of the most difficult to air seal sections of any building is the rim joist area, the band joist rim board area, because most conventional wood construction is platform framed, where you build a wall, then you build a floor on top of it, and then you build another wall on top of that. Because air sealing the rim board is rarely done well, and conductively insulating is really difficult, particularly on the side where all the joists land, we just decided to eliminate the rim board. So the picture on the right you can see is the first floor wall is up, they're putting the second floor floor joists in place, and then the subfloor is going to go on. And then the second floor wall goes up from there. And this is the section view that's on the left. It does a few nice things. We don't have the flaw of the rim board. And also it reduces the amount of hardware I need in high wind zones, because my subfloor, my horizontal diaphragm, is directly connected to my vertical diaphragm, my walls. So structurally, when we're on Nantucket and Cape Cod and the rich end of Long Island, where they got very high wind loads, basically each story of the building is its own shear box, stacked one on top of the other. So we wind up with less Simpson hardware and fewer fancy fasteners and things holding things together. This is our conventional panel joint, and we'd asked before about what holds the panels together. This is the most common in-plane panel joint. No thermal bridge, and the red dot indicates where we're injecting spray foam. We make a dado in the middle of the panel to allow the spray foam to expand lengthwise, and we drill and fill by injecting spray foam into that foam channel 8 inches on center. And we know the foam expands way more than 4 inches in either direction. When we have a beam, we can mortise the beam into the panel. If the loads aren't that high, the panel alone will carry it. If the point loads are higher, we embed a column within the panel.
Paul?
Yeah.
What kind of shrinkage do you have in those joints? Does the foam pull back at all over time?
If it does, you can come and shoot me. There can be shrinkage of the foam core when it's manufactured wrong. That is why some of our longtime competitors are no longer in business. The shrinkage that we see on our panels because we work very hard, is somewhere between 0 and nothing. A 6.5-inch panel overall should be 6.5 inches forever. The OSB can change thickness with moisture content, but if that's actually happening, we're already got other bad things going on and something's already gone wrong. Core shrinkage should be a once every 100-year thing. The molded in place urethane core panels do have shrinkage when they have manufacturing problems, but that's why nobody makes them that way anymore, except for a couple of diehards.
As per the last picture that you showed of the joint where you're injecting the spray foam, have you ever forensically gone back to some of your older buildings and look how that spray foam is held up in terms as a sealant between the two panels?
Hundreds and hundreds of times. between renovations on buildings we did 20 years ago and over the last 14 years, my boss and I have accumulated, is getting on 200 individual site inspections where we've cut walls open. And because when you're using a spray foam to air seal something, the spray foam itself air seals very, very well. The place where things usually go wrong is the interface between the spray foam and the other material. Spray foam against wood is not an effective air barrier in the long term, which is why stick and spray foam is fine in Atlanta, and in the Northeast it is troubled. When the spray foam is sealing two pieces of plastic foam to each other, the wood expands and contracts with moisture content, not so much with temperature. Plastic foams expand and contract with temperature and not moisture content. The coefficient of expansion between urethane spray foam that we use for our air sealing and any of the foam cores we use, especially the polystyrenes, are so similar that everything moves together. And to be honest, once we pull the nails out of the spline in this detail, it is still a bastard to get everything apart. The long-term track record has been very, very good. There are a fair few people out there that are using a mastic, a caulk type material between the foam cores, and that has much more mixed results. We've been using this system for a long time because we have enough track record with it that we know that the failure rate's extraordinarily low, so long as your installers give a damn. I've got another seminar on building durability of any high performance wood building. And the holy trinity is design, materials, and installation. And you can't screw up any of them. If you blow one of them, you're toast anyway. When installed conscientiously, the failure rate is extraordinarily low. And we've got thousands of projects out there.
Paul, are these splines or battens, are they glued in with polyurethane as well?
No, they are fastened in with nails.
Okay.
Basically, we do the structural connection with wood and nails, and the spray foam is only there to act as our, thermal barrier and air barrier. It does do some amount of work holding things together, but in the engineering, we assume that contribution is zero. It's not, but it's hard to quantify.
Thank you.
This is the normal sill detail, whether it be on top of a foundation or on top of a slab. The bottommost piece of lumber is almost always pressure treated. And you can see the red line of sill seal or whatever your water migration barrier of choice is. When we're in control of the foundation design, or we're collaborating with somebody who's into the whole integrating everything as a system, we ask that the J-bolts stick out of the or long enough so the J-bolts still have proper embedment and stick out of the concrete 4.25 inches, so we can use them to bolt down not only the PT sill but the shoe, which is the piece of 2x that goes down first with the panel keys over top of. Wiring, there's no stud base. How do you wire a SIP house? Oh my God, what are we going to do? It's not rocket science. The thing that I tell people is that I'm wiring my own house. This is a fully SIP house, and I'm an engineer, and I haven't even hurt myself once. It's different. It's weird. The first outlet or first light switch is going to take half an hour, but every electrician we've done tech support with, after the second or third one, they're like, oh yeah, I got this, they're fine. It's all about overcoming the weirdness of being different. Also, we can do embedded wire chases within the panels, vertically and horizontally, or you can drill your own with a long, flexible drill bit that we call field wiring. You kind of stitch your way from place to place. In general, the scheme is you do your horizontal runs through the deck and jump between floors through interior walls, and then in the panels, Most of the time you're doing perimeter outlets or light switches next to doors most of the time. So you do your horizontal runs in the deck system and you jump up or jump down to the fixture that's nearby. It takes a bit more wire that way, but there's more than a few local electricians that have done a few SIP jobs, and some of the older guys like doing SIPs better than doing conventional framing. I think it's because they're not that young anymore and they spend less time on their knees drilling sideways. Plumbing.
Sorry.
Yeah, good.
On the electrical, once you put in the type of boxes that you put in for the outlets in the perimeter wall,
Yeah.
are they a shallower box or are they?
Nope, full depth box. Actually, I happen to be in a convenient place. Let me go back. Can you, wait, where's my camera? There it is. Can you see that?
Yeah.
That's the box.
Okay.
Straight from Home Depot.
So how do you, when you've got the 8 1/4 or 6 1/2, it's giving you the 23 or 30. And now you're gouging out what, 3 inches? How does that?
Yeah, you hollow it out to the depth of the box plus a little bit for tolerances.
Right.
And yes, we've thinned out the insulation in that area. However, the number of square feet of that over the course of the whole building is 0.0001% of the surface area of the building.
Mm-hmm.
So the contribution to heat loss is lost in the noise of rounding errors.
Right.
And so long as we maintain our air barrier and we have some insulation between the box and the exterior skin, the back of the box is still within a degree or two of indoor temperature.
Yeah.
So there's no condensation to happen.
Right.
When you poke, if you have somebody that goes way overboard and
Right.
digs all the way back to the other skin of the panel,
You got a problem.
if your electrician kind of got out of control after the roughing is done and the wires are pulled, run around with a spray foam gun just to make sure.
Cool.
We've seen a broad variety of creative interpretations over time. So we've mostly been around this block before.
Cool. No, this is good. This is good. Whether you're using a shallow one or a deep one, I think the main thing is the air infiltration, and there's no air infiltration here. I mean, it's a solid piece.
Absolutely. And you saw earlier, I had a slide that showed the orange silicone electrical box condoms.
Yeah.
Those work. Electricians universally hate them, and once in a while they actually get installed right. Those work, but this is more robust and easier to do on a construction site environment, because you just tell them, don't dig all the way to the back. Just dig deep enough so you can put the box in and call it good.
Right.
And these are all 6 1/2 inch walls, and I'm using the default 3 1/4 inch deep boxes that sit in a 2x4 wall.
Yeah.
So I still got a couple inches to go.
Yeah. Cool. Thank you.
I'm a mechanical engineer by education, so plumbing is near and dear to my heart. The greatest achievement in the history of mechanical engineering is indoor plumbing, and nobody cares until it stops working. But with plumbing, how do you run pipework in walls? Like, well, exterior walls, you don't. Not in our climate. So I don't have any real good details for that. You can sneak a vent stack in if you have to, but if you can design yourself out of that hole, that's the way to go. Yeah, this is the topic that I do most of my presentations on, because it wraps up performance and durability and long-term health issues all in one topic. It's an incredibly broad topic, and anybody that says they understand this completely or uses this as part of the name of their company may be taking themselves too seriously. It's a very complicated thing. It's very site-specific and building use specific. I've seen buildings that should be building science disasters, but because the house is owned by a retired couple who have never taken a shower longer than 3 minutes in their life, the house is fine. I've seen other houses that should be in pretty good shape, not perfect, but not too bad, but they've got 4 teenage girls, so the moisture loading is Hell, it would have been better if they had an indoor swimming pool. The building has to fit the use, and the materials have to fit the use. And maybe this is the paranoid engineer coming through, but I'm not comfortable I can predict the use of a building for forever, so I tend to be a bit more on the conservative side. So in any wood building and anything that involves biology, everything revolves around water. And maybe Carol's in good shape. I don't know what part of Texas you're in, but in the Northeast, water is not one of our problems, or the lack of water is not a problem. And that's where most of our durability problems come from. The other thing is that with a lower performance building, you blow a lot of BTUs out through the envelope, and that performs a very useful drying function. By reducing the heat loss and reducing the energy consumption, we're also taking away a very important maintenance mechanism. So as the building gets tighter, of whatever kind of building, SIPs or stick and spray foam or double stud walls or I-joist studs or whatever, I don't care. As you reduce the heat loss, water management for the building envelope and the handling of exterior water are critical for the long-term durability of the building. And as we tighten it up, we have to get more conservative because we don't have that plan B of just blowing BTUs through the envelope to help dry things. Some things are a design failure, says the engineer with no taste who never does architecture. Yes, Carol, I can see you waving, but you're muted.
Is that how I'm supposed to raise my hand? I don't know if there's some tech way to raise my hand.
Actually, I think there's a button somewhere, but that's okay. We're good.
I can't see it, but anyway, down here, the big problem is humidity. It's huge. I mean, that is a big problem. Right. And since a lot of this good science in the Northeast, I don't hear a lot about controlling humidity.
Well, actually, we do a lot of work controlling humidity in our climate here, except that in the case of the wall or the roof, everything is backwards. For us, the cold side is the outside. For you, it's the inside.
Right.
So I'll probably say somewhere through here that your air control layer, your air barrier needs to be on the inside of the assembly. What I really mean is your air control layer, your air infiltration prevention layer, to prevent condensation within the assembly, your air control needs to be on the warm side of the assembly. So for me, that's on the inside. For you, it's on the outside. Fortunately for you, doing air control on the outside is dead easy compared to the inside because you don't have abutting interior walls and all that other stuff going on.
Just kind of random.
Right. Here, our interior air control layer is busted up by interior walls. Every light fixture, or 99% of the outlets and light fixtures in the whole house are all on the interior side of the walls and roof, all of which screw up our air barriers. When you're in a cooling climate, the warm side is the outside, so doing your air sealing from the outside makes all the sense in the world. So your job is a little bit easier than average, but if I say inside versus outside, please excuse me and translate that into warm side versus cold side.
Well, thanks. That really clears it up because I read a lot of things and that I've always been confused because now I know why I get confused. Okay. Thanks.
Yeah, absolutely. And the other thing is that anybody that says they've got the perfect weather protection system or the perfect insulation system that works over the whole country probably also has a bridge for sale, because the ideal solution in Vermont is not the ideal solution in Texas. I've no doubt the stuff that we do here will absolutely work and perform very, very well, but it's probably not the most cost-effective thing, and it's probably overkill in a variety of ways. You can build anything in Tucson because it's warm and dry. When you have large temperature swings over the course of the year, and around here we get 100-degree temperature swings every year, 100 plus, 120 some years. That's where it starts getting tricky. So if that answers your question, my slide here is I was diagnosing why are the panels on this house a mess in this area. Well, one, on the left-hand picture above the ladder, you can see the bottom discharge area of a relatively large valley. So every time it rains, you get a fire hose coming off of that valley. And you'll notice that window up on the second floor doesn't match the rest of the windows in the house because it's been replaced 4 times until they found this magic material called vinyl that doesn't rot. It doesn't work very well, but it doesn't rot. The other thing that's going on is I noticed they have the dryer vent of this house with a family of 5 with little kids in it. So they do 11 loads of laundry a day. The dryer vent is tucked into the corner. You can actually see the dryer vent in the right picture actually can be seen in the left picture if you look down at the bottom. So when you've got this perpetual plume of humid air coming out of the house, it doesn't do anything good for the structure of the building, particularly when you've not really followed all the recommendations for moisture control from the outside. So, you know, everything, weather is statistical, the use of a building is statistical. So to me, long-term durability is quite statistical, and the only thing we can do is buy ourselves levels of insurance. If you're in Tucson, you'll be fine. Whatever you do will be okay. You're on the coast of Maine with a house with young kids in it, we should be careful. This was a design failure in that incompatible materials were specified together. They put a peel and stick membrane over their panels, and 15 years later they need new panels because even the manufacturer of the peel and stick membrane says do not apply this over wood sheathing that has insulation directly behind for use on cold roofs and vented roofs only. They didn't do that, so now we're into a heinously expensive repair, not that long into the future, because nothing dries to the inside in the Northeast, in the North. Everything dries to the outside, and when you put a hydrophobic barrier on the outside, surprise, surprise, it retains water. And it's fine for a while, but over the years, the moisture content of the wood rises from 8%, 9%, 10%. Eventually, you hit to that magic 20, 22% range where fungus growth takes off. And then after a couple of years of that, it's all over but the screaming. By the way, just so everybody's got some reference, the reason kiln-dried lumber is dried to 19% moisture content is because they want to prevent the lumber from going fuzzy in the lumberyard. We all know that kiln-dried lumber is not particularly dimensionally stable yet. It's not dry enough. So why do they only dry it to 19%? It's because almost all of the species of fungus that eat wood don't grow in wood that's less than 20% moisture content. You can see some remarkable movement in the wood, especially in like the high plains in Wyoming and things where the steady state moisture content of wood inside of a building is 3, 4, 5% moisture content. When it's a tree, it's 60. When they dry it down to 19%, nothing grows, but it doesn't take much water to bring the moisture content back up so that it does start growing again. In this case, when you have, you know, the OSB, when we get it, because it's been through a 400-degree press, is 5, 6, 7%. But if you trap water in it, it will slowly grow over time. And no matter what the species, unless it's some sort of tropical expensive thing, once you hit 20, 25, certainly 30%, biology takes off and the degradation of the wood grows at a population growth curve. You know, 1, 2, 4, 8, 16, 32. And then you rapidly get to the zone where I'm not half smart enough to figure out what the remaining structural capacity of the wood is. So our recommendations are use a, put your air barrier, treat the warm side, sorry, not the inside, the warm side of your assembly as your air barrier. And everything outboard of that air barrier needs to be of increasing permeance and not hydrophobic. All of these synthetic but very vapor open building wraps are great so long as you have enough heat flow to drive liquid water into a gas to pass outward through your Tyvek, Typar, rooftop guard, Triflex, whatever your building wrap of choice is. When you cut the heat loss to half or less of what it would have been otherwise, and you're relying on heat loss as on the north side of the building, the only thing that drives liquid water into a gas is heat loss, and we've cut that in half, the building dries half as fast. So the paranoid engineer built his own house with old school tar paper for building wrap and window and door flashing. And then create a capillary break between the roofing and siding and the sheathing of the building, be it strapping or home slicker, or rooftop guard, ripped strips of plywood or 1x3s, I don't care. Just break the capillary effect between the backside of your sheathing and roofing, but between your roofing and siding and the sheathing itself, to allow airflow through there. And if you're using wood siding, it doubles the life of your paint job, because the thing that makes paint fall off is the difference in moisture content between inside and outside. That's the quickie version. Like I said, we don't commit architecture. You send us plans, and from a design standpoint, it's probably easiest to just assume that we make infinitely large panels of whatever thickness you want. Pretend we make them 100 by 100. Let us whittle them into little pieces so that we can actually get down the road and assemble on site and handle the structural stuff. What we really do is we take your designs and we break it down into what we call surfaces. And a little Cape Cod is 1, 2, 3, 4 surfaces around the walls, surface 5, surface 6. And then we whittle it up into panels. I think the record is 93 surfaces for one job, and it was a house with the most gnarly roof line there ever was. We did it, it fit, everything worked good in the field. I won't say there wasn't some foul language in the design office, but we did it. We'll break it up into surfaces. That's when we can get some real good cost numbers, so we know how many square feet of panel we're into, and also what the other structural and other details we have to build in. And then we design the panels. We make panel drawings that are our understanding of what you want us to build, or what you want us to supply materials for. And up through this point, design changes are basically free. Once you say, yeah, that design is good, that's what I want you guys to do, we work really hard to make any design changes as painless as we can, and most of the time they are free. But once we start making materials and cutting them up, if you decide you need your eave side walls to be another foot taller, that may not be free anymore. Once we're into manufacturing, and then installation, whether we do it or you have somebody do it. This building was also one of the character building ones. It's actually a rich guy's observatory for his telescopes on top of the mountain he bought in northern New Hampshire. But none of the walls are square and none of the walls are plumb. The largest challenge was making the adjustments for the concrete that was mostly right, but they took some artistic licenses because concrete guys don't work to fractions of an inch. Often they don't work to whole inches, much less fractions of an inch. We talked about cost before. This was a building that looked like a house in Keene, New Hampshire. It was actually going to be a dentist or orthodontist office or something, but it looked like all the other houses in the neighborhood from 120 years ago. The construction company figured it was going to be $200 per square foot of floor space, all built, ready to move in. Conventional, stick and infill and rigid was $27 a square foot. We were $31 a square foot. So that's $4 a square foot difference. So we're going to say that's 2% of construction costs, roughly. There's another offsetting cost, and that's time on site. And I don't know how to quantify that well, but the professional builders make a real big deal about how long each trade is going to be on site, because that is real money. So there's somewhat of an offsetting factor there. And the main difference was the fuel consumption was half. So, like I said, strictly from an economic only standpoint, in our neighborhood, a break-even payback time of 4 years is really long. We've had some that are less than a year. Usually it's a couple of 3 years to where we break even cost-wise. And that's even including the extra mortgage interest from the slightly higher construction loan. And whenever we did that analysis, we assumed fuel prices were going to be constant forever, which is not a great assumption, but we're rounding in the other direction just for this analysis. And I think the break-even point was about 2.5 years. When we do our own structural design, we do have a competitive disadvantage in the world in that I'm enough of a jerk to actually think we need to be code compliant and not say, builder says it's fine, it'll be good. The other thing is because one, I'm kind of allergic to bouncy track house floors, and two, I don't want to care what kind of tile you're putting down. Our normal floor design stiffnesses are way beyond code minimum. And you could put down 2-foot square terrazzo if you want. I don't care, the floor's still stiff enough. Also, we provide a lot of building science support, and not half enough mechanical guys and heating technicians call me. And I've seen some really tragically large heating systems installed that are fine, except the machine's beating itself to death because it's firing up and shutting down. You know, it runs for 5 minutes and shuts down. And then an hour later, it runs for 5 minutes and shuts down. And the machinery doesn't last that long, but they don't burn any fuel. As I mentioned before, our panel layout drawings that we send out for review are our understanding of what you want us to build. If it's not in the drawings, that means we didn't think we were doing it. We're very drawing centric, and we've got a team of designers that are first rate. Manufacturing, we sell panels as raw sheet goods. You can tell us just put so many 8x10s and so many 4x16s on a truck of whatever panel specification, no problem. But most of the time, about 90% of our work ships out fully pre-cut, where we've done a panel design, all the rough openings are cut out, all the panel edges are prepped for blocking, and you basically do play Legos on the job site with a crane. And more often, especially when it's our install, we're assembling big lengths of wall on the truck, and we've got one of our trailers modified so that we can stack up 10-foot tall by 28-foot long pieces of wall as one piece. And we've done jobs for simple jobs where the thing that limits how much time we spend on time is how fast the crane goes back and forth. And that's it, yeah. When we do the install, it's a crane and usually 4, 5, 6 guys, depending on the size of the job. And if it's somebody else's install, we will rent you one of our master installers to coach a rookie crew through the process. We've learned that having project managers do on-site training, having project manager to tradesman training or engineer to tradesman training works okay. Tradesman to tradesman works really, really well. So we usually send out Joe or John. Both guys have led, honestly, over 1,000 SIP installs over the past 20 years. We got guys with us that started working at Ford in the late 80s and have been there continuously since. So that's my normal shtick. I hope there's questions. Watching the videos here, it seems like nobody was sleeping, best I can tell. But please ask away.
Go ahead, guys.
Shoot, please. I try not to be boring, but I do the best I can.
I have a question.
Yeah, go ahead, Carol.
So when your crew comes out and does the whole install, I take it SIPs are not interior walls. Are you just doing the exterior and then you stop, or are you doing interior also?
That's a good point. You'll see this when we get to the panel drawing level. The thing that we normally do, like this project here on the left, or actually I can pull up some pictures. I'll use my own house, what the hell? Let's see. Cat's unhappy. When our crew arrives, normally there's a naked foundation, and when our crew leaves, it looks like your house, only it's all OSB colored inside and out. Where there's interior walls, we don't often build load-bearing interior walls because I've had too many people change their mind later and have cut holes in what I know is a load-bearing wall and totally freaked me out.
Yeah.
So what we normally do is we'll have a glue lam column strategically placed to hold up the second floor and the roof and whatever else we need that will be within an interior wall that'll disappear when the interior walls are built. Because we've learned that most of the time, not always, but most of the time, Joe the carpenter who's got his sawzall out and is cutting out a door opening or whatever, most of the time they'll stop when they get to a big hunk of engineered lumber because they think that might be there for a reason. So when, actually I don't know if I have any pictures of the inside. Oh wait, you can't see this thing. Hold on. I got to change my...
Yeah, you got to change the screen.
I got to change my screen because you're only looking at one application. Let me go back to the app here. If I can. How do I stop sharing my screen. Now I want, I think I crashed my thing, Gio. Can you guys still see anything?
You.
Yeah, we can see
You see me, okay. Right.
You're good.
Where did my, oh, here it is.
Oh, yeah, there it is. Yeah, this little greeny thing.
Uh-oh. I totally lost the thread.
When you go to share, when you go to share a screen, it'll.
I'm not getting. Oh, here we go. Gotcha. I lost my window Geo, but now I got it. Here's my whole desktop. Share that.
There we go.
And now you should see everything on my desktop. Let's see. So yeah. I mean, this is what it looks like going up. And you can see, if I zoom in over here, you can actually see beam pockets already prepared within the panels for when they have the walls up and then when they're ready to work on the second floor deck and the beams drop into those pockets. That's how panels arrive. As you see, they're all serial numbered. This top panel here is Surface 3, panel 14 on Surface 3. And away we go. We do our own insulated headers. So this is looking up at the inside of my front door, rough opening. And because of the loads that are there, we've got 3 LVLs carrying the weight. But in between the first and second LVL, we've got 4 inches of XDS insulation because thermal bridges suck.
What is an LVL?
Laminated veneer lumber. Sorry, engineered lumber beam. Sorry. Yeah, let me know if I slip into crazy jargon. One wall is down, and they're preparing to put the mating wall abutting it, as you can see at the corner of the building. There. Surface 4, panel 5, connected to surface 6, and what they're doing right here is sliding the spline in lengthwise into the slot in the bottom of the panel so that when they stand it up, they can nail it off on both sides. And that's how you join panels together in the same wall or roof surface or whatever. Here actually you can see here's a cross section of, this is a piece of panel that at the moment is upside down, but it's over top of the front, over top of the back door. And the place where the guy's got his gloved hand is where the top of the door will mount. Like I said, it's upside down in this view, but he's fastening the insulated header into the wall panel that's above the door. if that makes sense.
And are your windows handled the same way?
Yes. When we need a header, we do it with an insulated header. Most of the time, windows are small enough that we don't need anything. This is a wall that's about to be tipped up, and you can see this across this big window. Here's the insulated header embedded within the panels. Because of the loads and where the weight of the building goes, I couldn't do it with the panels alone, so I had to use an insulated header. And that's the wall stood up. Let's see, what else do we have?
So I think I misunderstood. So you do not put the interior walls in, or you do?
No, we don't build interior walls at all. We'll hide a post. We'll put in a structural post that will get hidden into an interior wall.
Mhm.
But that's about it.
Wouldn't it be
We try not to build them.
Wouldn't that be easier to put them in while you're assembling the house?
It can be cheaper. It's kind of a wash either way, because usually our crews are staying in hotels and things. So we're relatively expensive labor. We'd rather let local labor do that. Trying to see who's talking here. Because that was Mark, I think, right? Framing the interior walls, non-load bearing walls, goes really, really fast. So we struggle to be competitive with it, particularly with our higher labor cost loading, because again, we're traveling and things. And we don't need to structurally. We try to design that out of our plan. So that way go ahead.
Are all the panels that you make SIPs, or do you make any prefab walls that are not SIPs?
All the things that we do are some form of structural panel. We do drywall clad structural panels, like, well, you can see in this picture a little bit, the roof of my living room is drywall clad SIPs. So it's a SIP with drywall bonded to the inside in our shop, because that's way more cost effective than setting up staging to have drywall hung after the fact on the ceiling. But drywalling the walls is so easy and cheap, it's more cost effective to do that in the field, or to have your local drywall guy do it in the field. Actually, you can kind of see here in this picture, I'll zoom in a little at the top. You can see the floor joists are hanging in hangers. They're open web truss floor joists. They're hanging in hangers rather than resting on top of the wall. So we don't have the thermal bridge of the rim board everywhere. The first floor walls go from the first floor subfloor to the second floor subfloor as one piece, making a nice continuous envelope and simplifying the structure. But you can see there's some interior stick framing going on in this picture, but it's pretty easy.
Do you do the windows?
No. Again, because of our higher labor costs, and also because the only way to install the windows properly is to flash them as they're being installed, our crew is long gone by then. When we leave, all the rough openings are there and all blocked out, ready for things to be installed, but we don't do the installation.
Okay.
It's just a construction sequence problem. This is my house, so I've got the whole thing all the way through.
So Paul, on your ceiling, it saved you having to put up the drywall, but you still have to do any taping, right? Or am I wrong?
That's right. Actually, if you can see, there is a drywall joint that will need taping right up here in the corner that I think you can see.
Right.
You can see the drywall joint there.
Right.
That does need to be taped and mudded after the fact, and Ford doesn't do that. It's just that, honestly, because these trusses are timber framed, and timber framing is done in green, when these trusses went in, they were 40-something% moisture content.
Mm.
So they were 6 inches wide. Now they're 3 and 5. I'm sorry, they were 6 inches wide. Now they're 5 and 5/8.
Yeah. Yeah.
If you drywall after the fact, when the timbers shrink, you now see gaps.
Right.
Right? If you drywall over the top, when the timber shrinks, it just reveals more drywall.
Doesn't matter.
And it works much better. So that's why, I mean, when we do timber frame walls, we put drywall up against the timber frame and then put a panel over top of it and then back fasten the drywall back to the panel for exactly that reason. So we can get the drywall behind the timber.
The timber frame.
We could do that on the roof, except it's tough for the install crew because if you step in the wrong place, you die.
Yeah.
So we glue the drywall to the panel and it flies in as one piece.
Yeah. No, that makes sense. I'm just thinking, I mean, you still have to have tapers or mud guys coming in and
you still have to mud and tape, absolutely.
Yeah.
Let's see, where does this line go? Oh, there's the window installation, flashing, and vented wall assembly going together at once. And to me, this is the proper sequence. Wrapping the whole building, then cutting out your rough openings basically prevents you from flashing the windows properly. Having done a lot of investigations, and Gio's seen some of them, I've got many, many terabytes of pictures of horrible repair situations. Window flashing is the single most common failure in any wood building, and particularly any high-performance wood building. And it seems that the state-of-the-art best flashing technology there ever was state-of-the-art for about 1950. Grandpa's way of folding the tar paper in with a piece on the bottom and then usually a shingle underneath it maybe, flash the bottom, the tar paper up to the bottom of the window, flash over the bottom of the, make a base flashing, flash between the windows, wrap into the rough opening, put the window in, and then flash with your drip edge over top of the windows, absolutely works the best. And anytime people are talking about covering something over and cutting it with a utility knife and using some sort of tape to hold it together, yeah. If your design lifetime is 5 to 10 years, great. I kind of think buildings should be reliable longer than that. And in my case, I used ripped pieces of 3/4 inch plywood as my material for my vented wall. But you can use whatever you like.
Paul, did you say you did structural engineering work for buildings that you don't?
There you can see at the top of the window. Ooh, you okay?
I've lost.
Uh-oh.
Hello.
I got the microwave. Hi, everyone. Can you hear me? Hello? It says I'm using computer audio now. I can see. Can you hear me?
You're breaking up a lot.
Oh, there we go. Now everybody's coming back. So we lost my screen share, I think. Sorry, I had a Wi-Fi issue on my end. See if we can get this back. All right. Can everybody hear me okay?
Yes.
Okay, sorry.
Hey, Paul.
Yeah.
In this picture here, could you walk us through what you were just explaining about the flashing?
Sure. Let's see. We're looking at the whole window, right? Actually, is this the best picture? I don't know. Let me see. Oh, that's even better. Here we go. We'll use this. So what we did was we flashed up to, that's even better yet. We flashed up to the bottom of the window. We ran tar paper up to the bottom of the window. then you can see the piece of tar paper that is coming out from the bottom of the window comes from the bottom of the rough opening over the outside of everything. And that's the piece of flashing kind of in the center of the screen right there. Then we ran tar paper between the windows, from the side of the window to the side of the next window or door or corner of the building, whatever. And that wraps into the side of the rough opening. And the only tape in the whole assembly is right at the 3D corner. But you can kind of see they've got the bottom done, and they're working on the sides now. And then the window goes in with your spacers or whatever else you're doing. Let me know if I'm jumping around too fast, but and then at the top of the window, we do a metal drip edge and then tar paper across the top of that. So everything shingles its way to the outside. The place that water is supposed to be is back out in the environment where it came from, not up against our building. So yeah, does that make any sense? Does that kind of answer questions?
Paul, is it my understanding that you don't believe any sort of tape seams are long-lived?
Haven't found one yet. There's all kinds of fancy stuff, especially with some really, really awesome marketing plans behind it. But so far, I can't find anything that works as well as old school tar paper flashing from 1952. The reason nobody does it, or the reason most people don't do it, is because it's labor intensive. And if the goal is to build with absolutely minimum cost, this is not the way to do it because it takes time and actually requires people to pay attention. For every building that Ford Panel does, the production builders do thousands. So the big material manufacturers don't really care about our market. They're the Pulte homes and the KBs and things like that are what really drive their sales. So they cater their market to them, and what they care about is cost of construction, period. That's not really the market we're in, so long-term durability does matter to us. And I can't find any of those materials that last half as long. And when you start seeing enough data points, you see enough troubled buildings, you see really clear trends. And every synthetic building wrap I've ever seen, there have been real issues. And I can't find a tar paper covered building with issues that weren't caused by something obvious, like they didn't flash the bathroom vent stack or something easily identifiable. There's no systematic failures. And even if I didn't understand at all, even if I didn't have any opinion at all, so what the mechanism is, just the preponderance of data makes it really, really clear.
Paul, when your crew leaves the site, it's not watertight at all. The structure isn't watertight.
That's right.
Is there a problem between the time you finished and it's watertight? And what kind of time frame are you talking about?
By the book, all the materials we're using are good for 30 days of exposure during construction. The last thing to go on is the roof. If you can have your roofers follow on in the next couple of weeks, we're going to be fine. The record, and not that this is recommended, but the record that I've come across between when the SIP building went up and they put the siding on was 23 years. Because the young couple built their own house, had finishing the house as they were expecting their first kid, and then life happens, and then their oldest daughter says, "Hey, Mom and Dad, I'm getting married and I'd love to have it at your house." And Dad says, "Wow, I ought to finish the siding." not recommended, but it was okay. The OSB was really gray from UV degradation, but they had decent overhangs and it was all right. Yeah, you should have the roof on within a month of the panel install. You know, next couple of weeks is perfect. And then close up the building before weather sets in. There's been some really tragic cases where they got the roof on and then ran out of money or a disaster happened or whatever. And then the building sat with no doors and windows for a year or two. And just from wind-driven rain and everything else that goes wrong, it's not a happy situation. Once you start, you got to be ready to finish.
Right.
But either way, that's, you know, this was, let's see. The panel install was, the panel install was going on March 30th. And the roofing install is April 14th. So 2 weeks is what I was able to pull off schedule-wise. And when things progress like that, the odds of trouble are 0. Any other questions? Has to be something. There's no way I'm that 0.
To finish the house off, I guess you'd really want to work with a contractor that's done SIP construction. You know, a lot of it probably. Is that
there's not that many of those. And to be honest, yes, I suggest that everybody work with an experienced builder. There are people that have GC'd their own things. And the people that have been successful at it have got very strong project management skills of whatever kind of project management they're good at. Project management is good project management. But working with a builder is usually the cheapest solution for most people. Among other things is that you get his Rolodex of people that want to work with him in the future. And it's much easier to get a plumber or an electrician's attention when this is a builder that does a couple of houses a year and there's repeat work here versus a homeowner that's doing everything once. So what are the odds you're going to get their attention of the good guys kind of thing? The role that Ford usually plays is of a specialty subcontractor. We're involved in the design end, usually the structural end. But then when it comes to the on-site work, again, the first job we normally do is put the sill down. And then when we leave, it looks like my house did when the roof is going on. It's your house, only it's all OSB colored, and you need a real builder to finish the rest of it. The other 98% of the work of finishing the building is still to go. You can do it yourself. I'm doing now. It takes a long time. I'm slow and picky, but it's totally doable. The thing that is easy to neglect, particularly when people are working to, when workers are building to a price, is attention to detail. And the other thing that drives into that is it is so much cheaper to design first and build second. And when I say design, I mean design means decision making. Design is the art of compromise. You can see that because I knew where they were going to go, the hose bibs were actually mounted. Like I knew the drawing said where on the wall the hose bibs were going to go on the outside of the house. So the carpenter actually trimmed them out properly and actually have a drip edge over them. Maybe that's a little obsessive, but I'll bet you 30 years from now I'm going to be happy about that. And of course it's all painted purple now like the rest of the house, but so it doesn't show up as a white block. It doesn't look like that. But this is everything in process coming together. And I don't think I have a picture of it, but the dryer vent, the intake and exhaust for the ventilation system, the boiler stacks and everything was all on the drawings before the foundation was finished. And I realized a long time ago that I asked the Ford panel guys to do it, and they would for me or for anybody. They put the top couple sections of my wood stove flue in the panels before they left, because I learned a long time ago that roofers are much better at roof flashing than plumbers or wood stove guys. All of the penetrations through the roof were in place. Not only was the hole there, but like the flue was there before the roofers showed up. So they did their thing around all the work there, which, among other things, if anything ever leaks, it leaves me with one person to yell at, because nobody poked a hole in anybody else's work. And that's what I really mean by design first and build second, is that you can make little tweaks to the construction sequence to make things simpler and to really improve the final end product.
Paul, what material is your siding?
Cedar. The whole outside of the house is wood. Cedar siding, cedar trim, and the windows are mahogany. FSC certified mahogany, but mahogany. The only reason I can get away with high-end specifications like that is not that I'm in the 1% or anything. I'm absolutely not. But it's a 1,200, 1,300 square foot house. There's just not that many square feet. There's nothing that drives cost more than size. Oh, here we go. This is what we do in our shop. This is what the pre-cut guys do. So you get the idea. This is the pocket where one of the timber trusses sits, or it's half of it. And then the other panel makes the other half. And I don't know if you can see, but it's hard to see, but because I've got relatively thick walls on the first floor, I got 10 1/4 inch walls on the first floor because I wanted the angled window reveals. The post that holds up the timber truss is only 3.5 inches square. So basically in the surface spline joint I showed before, we've got an inside spline and an outside spline. Well, at this joint, the outside spline is a 4x4. And that's what's carrying the point load from the truss above. But I've still got yay much foam in between that spline and the interior face of the building. So not a thermal bridge, and I'll never be able to measure the difference that little loss of insulation means in the operational cost of the building.
Paul, is there any recycling of your foam waste?
Yeah, we do the best we can. Some of our foam is easy to be recycled because it's clean, but right now nobody wants the foam that was right up against the OSB because the glue is infiltrated into it. So that winds up being burned into electricity. So at least we're getting the fuel back somehow, as with our wood waste. So we'd like to recycle more, but to be honest, the boss told us a long time ago, it's like, we want to recycle everything we can. It doesn't have to be a financial winner. It just can't be a financial disaster. And that's exactly what we're doing, is everything we responsibly can. There's a stack of insulated headers ready to go.
Paul, you said that you got the beveled jambs on your wall?
Yeah, yeah.
Was that done in-house?
Yes.
Not on site,
That
right?
also caused some foul language in the pre-cut shop, but we did it, and I like it.
Oh, no, they're nice.
Let's see, here we go. That's looking out through one of my library window rough openings. So basically they're 10 1/4 inch walls, but all of the window jambs are as if it was going in a 2x4 wall. Mm-hmm. And then I brought out the angle from there. And to be honest, to get that feature is the only reason the first floor walls aren't 6.5 inches thick, just because I wanted that. and I actually priced it out that it was cheaper to go to the thicker panels than it was to do 6.5-inch panels with a 2x4 or 2x6 framed wall inside. So the cheapest way to get that deep windowsill, cathedral-esque, splayed window reveal effect was just use really fat panels, and I got a fuel savings as a bonus. Oh, here we go. This is a door. This is a wall laying flat on the floor, and we're looking up at the bottom of what I think is my front door rough opening. So the windows are actually installed flush to the outside with the angled reveal on the inside. The doors are flush to the inside, and this wall is laying on the deck, exterior up.
Okay.
And you can see that beam or post number 20 is carrying the insulated header above. And that all was prepped in our shop. And the guys just assembled the pieces together and stood them up.
How much of a upcharge is that to do something like that? Relatively.
Let's see. What changes is our pre-cut charge changes.
Right.
And our pre-cut charge would go up 5 cents a square foot-ish.
Right.
So 1,300 square foot house,
yeah,
2,100 square feet of panel, 2,100 times 5 cents.
Right. It's not
free, but it's not that bad.
No, it's not bad. Not a bad trade.
Actually, you can see here that in a void space they injected spray foam into the void, but also you can see the gray, kind of a slate gray panel mastic spooging out between the 2x there. That's the sealant that we use between pieces of wood for air sealing. We use that mastic because remember I talked about how the spray foam works really well for foam to foam or to fill voids. When we're actually looking for an air seal, because wood is dynamic, we use a panel mastic that it's not construction adhesive. It does not harden. It stays pliable forever. It's kind of got the consistency of silly putty. It's a little stiffer than that. But as the wood expands and contracts with moisture content, it moves with it. It's not rigid. And that's why it stays air sealed.
And what do you know about the longevity of that?
The manufacturer claims 50 plus years. We have 18 years of experience, and so far I don't know what the lifetime is because we haven't gotten there. Fortunately, once the rest of the building is all wrapped up, the air leakage, even if that mastic wasn't there, is going to be very, very small. So the odds of long-term durability problems are pretty small. I won't say never, but I'm not sweating it much, and I'm about as paranoid as they come. And I've been with Ford for 14 years, and I could totally collect my gold watch from there. So the boss has got a very long-term mindset, and I like that a lot, and so do the rest of us. The other thing we did was, in my library, if you can see, I planned on window seats. So you can see actually the very thick walls, but then the wall below the window is actually thinner to make room to have a small windowsill and a built-in window seat. All these neat little things you can do when you design first. And we do all of our work, and I hope all of you do all of your work in real 3D models, because that's how you can tinker and play with all this stuff before it actually exists in the real world. Electrons are cheap.
What do you use as your modeling program?
Old school AutoCAD.
Nice.
It's terrible, but it's very flexible. And honestly, the reason we use it is because it's kind of the lowest common denominator among all of our, I think we did jobs for 90-something different companies last year. So we need to be able to talk easily to all of them. So that's why we use that. I wouldn't if we didn't need to connect with our customers quite this way, we'd probably use something more modern, like CAD work or Dietrich or something.
Cool.
Yeah.
That design
Anything else I can help anybody with?
That design system that you use talks directly to the factory then? The data goes from
the data that goes from our design office into our shop is printed drawings.
Is that right? Wow.
We are not CNC anything. They're not flexible enough. We could spend $1.5 million on a CNC machine that does half of our production, but we still need the same guys to do the other half of our production. And all of our competitors that have CNC equipment have more people and more draftsmen doing less work. So we would invest in machinery tomorrow if we can make a business case for it. But because we don't do production building and because we don't cater to the tract house world, we're not doing the same thing every day. We need infinite flexibility. Oh yeah, here we go. I mentioned everything was prepared. All the penetrations in the wall were prepared beforehand because they knew where they're going to go. So the round hole on the left is the intake for my ERV, and the little square block on the right is where the pipe from the solar panel goes back into the house. If you can see how that all works. And the back of my house faces due south, so we've got a couple of 4x10 hot water solar collectors in the back. I give up a little in performance by not having them inclined. They're dead vertical. They're flush to the back of the house. But I've got more, I don't need hot water capacity in the summer. And where I live, if they were inclined, I'd lose half of my heat gathering capacity in the winter because they get covered with snow and it takes a while for the snow to fall off. This way, no snow. There's a better picture of the back of the house. The big white block with the hole in it near the back door is the cover and actually the fan motor for the range hood.
Is that next to the solar panel?
Yeah, immediately to the right of the right solar panel, that big white block is for the range hood.
That doesn't affect the panel in any way, any performance?
No. It's just the exhaust vent for over top of the stove.
Right. Oh, okay. Okay.
It doesn't collide. The 3D model told me it wouldn't collide. It turns out it doesn't. It's close. Yeah. And then on the left wall, right at the second floor deck level, is the exhaust for the ERV system. And then above that, right below the roof, is the exhaust for the dryer.
Okay.
And for my windows, they are wood windows, but they're mahogany. You know you're dealing with a company that is used to doing performance work when you can choose which emissivity rating or which emissivity coating you get on the glass for which side of the building.
Okay.
Because the two little windows below the solar panels, that whole wall faces south. Those two little square windows below the solar panels don't get any shading. So those are very high reflectance, very low E glass.
Right.
However, the three windows above Eric get shading from the overhang in the summer, but are in my living room. So they don't have a low E coating. They are uncoated glass. So I get as much gain as I can in the winter, but I get shade in the summer because I've got a 2-foot overhang there.
Right.
And there are windows that are the same make and model of window that look identical, but they're different part numbers because the E coating on the glass was different because it was north side versus south side or something.
Okay.
And even with good guys, and I'm happy with the guys that did it, going around with blue painter's tape and labeling where each window goes so they don't screw it up makes a real difference.
Paul, are your windows triple pane or double pane?
They're only double. They're only double. The performance specification of the window is okay, but not special. They are not imported from Switzerland. But I've adjusted for that by not having that many square feet of glass. My glass fraction, if you took square footage of rough opening area divided by square footage of gross wall area, I'm at about 7.5%. As soon as your glass fraction goes over 10%, it doesn't matter what walls you use, it's the ROs that dominate the heat loss calculation. And just like we were talking before, that any knucklehead can meet all of the client's needs with a giant building. It takes real skill to make a modest sized building that meets their needs. In exactly the same way, any moron can get the interior lighting that they want with acres of glass. What takes real skill is getting the vibe and the interior daylight you want with as few square feet of glass as possible. And in my climate, I actually had my coworker Allison work out what U value of whole unit window do you need for a window to be a net winner in February. So while the sun is out, you're gaining. As soon as a portion of the time the sun's behind a cloud, and then all night, the window's losing. So what does your U value have to be to break even? And it turns out in climate zone 6, where I live, the U value is 0.16, which you can't buy. So in my climate, there are no windows that are thermal winners, unless you have thermal curtains.
I wondered about that. That's interesting.
It is remarkable. I mean, you hear things and read magazine articles and stumble across all these wonderful presentations at trade shows and stuff, but there are way more cheerleaders than there are scientists. So when you actually run the numbers, I mean, I've been skeptical of electrically driven air source heat pumps for forever because I don't understand mechanical engineering wise how they make any sense. So using the mix of electricity that feeds Vermont's power grid, part hydro from Quebec, part from wherever, part nuclear, part whatever, I asked, again, Allison, to put 1 BTU of heat in my living room with an air source heat pump driven by electricity. 1 BTU of heat in my living room costs X in carbon. Compared to my propane burning boiler that is in the basement and running right now probably, what does the COP of the heat pump need to be equal to my very basic old school boiler? And it turns out the answer is about 4, which you can't buy. The COP of air source heat pumps in the Northeast doesn't run 2.5, maybe 2.5. So from a CO2 emission standpoint, electrically driven air source heat pumps are net losers. You'd be better off running fuel oil or propane. Because the heat pump themselves is wonderful, the electricity supply to the grid and the grid losses are a disaster. And that wipes out all the advantage.
Those U numbers that you mentioned for the windows to be net positive or net neutral, is that just for the south facing windows?
Yes. So if you let the engineers run the world, and we have super efficient, really hideous, boring buildings, there would be no holes. Now, we'd all have to kill ourselves, so we don't build that way. But design is the art of compromise, and that's what I have to lay at the foot of the designers.
Maybe we can mount LED screens all around the house and just have cameras facing out.
To be honest, my vote is automatic thermal curtains. Those pay.
Thermal curtains from the inside or the outside?
Inside. So the U value of the rough opening jumps from 0.2 to 0.08, 0.06, like that.
What does that translate into in terms of R value?
R is 1 over U.
Oh, okay.
Marketing baloney. The reason they use U value to advertise windows is so that Joe Public doesn't understand how horrible they are. R value is 1 over U. U is 1 over R. So R4 is U 0.25. There are people that advertise R7 windows. Baloney. Most windows are R3, sometimes R4. A lot of them are R2. And you can see what that does to your heat loss count. So, anybody else have any other questions or complaints or anything?
I have an unrelated question from what we were just talking about.
Yeah.
So when is the air barrier and the vapor barrier the same, and when are they different? I don't understand what situations. I mean, I know the vapor barriers, air barriers, and that really confuses me.
When you get into buildings that are better than modern energy code minimums, I think most of the conversations about vapor barriers are marketing baloney.
Okay, that'd be helpful.
Because all of the damage I see is all driven by air leakage and the moisture carried with that air.
Okay.
The rate at which water vapor diffuses through solid materials like drywall is relatively low. The amount of water that diffuses through the drywall alone, assuming there's nothing else to stop it, through a whole wall of drywall, is still nothing compared to the water that's carried by the air through the electrical outlet hole.
Okay.
That's what dominates the equation.
Okay.
So, to be honest, so long as the durability doesn't, the absolute magnitude of permeance, whether it's a permeance of 1 or 0.1 or 0.01,
right,
doesn't seem to have that big an impact on durability nearly so much as where is the tightest thing and where is the loosest thing. And so long as the least permeable and lowest air leakage component is on the warm side of the assembly, durability problems are extraordinarily rare.
Good.
To be honest, 90% of the durability problems I see, probably 95% of the durability problems I see, are driven by outdoor water. Water infiltration from the outside and rain and that sort of thing.
Right.
When it's driven by indoor moisture, it's always because they have their air barrier and or their vapor control layer on the cold side. Or they think they put it on the inside, but they didn't deal with all those pesky electrical outlet holes and switches and doors and interior walls and stuff. So they thought their vapor barrier was on the inside, but it really wasn't. The vapor barrier was, you know, the sheathing on the outside of the studs, functionally, because it didn't have so many holes in it. But that's, for me, the cold side.
Okay.
I've seen houses where not only did they get condensation on the inside of their walls, they built up frost. And then the first warm day in the spring, they have gallons of water weeping out of every wall and every light fixture they have. Because the water condensed in there, but it was so cold in there, the indoor air was able to get to areas that were so cold, it didn't just condense, it froze. And they built up what they call rime ice on the inside of on the back side of the sheathing.
Wow.
And they thought they were doing a really good job by doing 12-inch thick I-joist stud walls. But because they didn't do an effective air barrier, and the insulation they used wasn't an air barrier, they used cellulose, they created a new kind of physics experiment that I'd never seen before, which is interesting, really expensive, but interesting.
Okay, so a good air barrier that's trying to the
The
warmer
air
side.
barrier has to be on the warm side.
And then that should cover the, don't have to worry about all this other stuff about the vapor. That takes care of the
Yeah.
vapor.
That's right.
And,
That's
and
right.
Paul, the warm side, cold side doesn't change in climate zone 6 from summer to winter?
It does, however, in one condition, the cold side's on the outside for 6 months of the year with a delta T, a temperature difference from inside to outside of 50 plus degrees. And in the other case, in the middle of the summer, the temperature difference is 10, 20 degrees, and it lasts for 2 months, and you have all the windows open. So it seems best to build for the most extreme, the strongest, most common case. If you're in, it seems to me that the dividing line between heating climate and cooling climate is Philadelphia, Washington, D.C., somewhere over there. If you're north of that, heating dominates. If you're south of that, cooling dominates.
So you're not a believer in these so-called intelligent membranes that allow.
You may have come across elsewhere in life that engineers and other technical people have got very complicated relationships with marketing people. This is one of the things. Yeah, intelligent membranes are right up there with cultured stone. Cultured stone is brilliant, marketing-wise. Cultured stone is cement. Cultured pearls are pearls. They're just formed. Cultured stone is cast cement to look like stone. An intelligent membrane is not. There's no decision-making going on. It has a set of physical properties, and hopefully they match the application you have. None of these membranes are directional. There's no inside or outside, other than maybe the surface texture, so it's easier for the roofers to walk on without sliding off. The whole variable permeance thing, to me, is baloney, because the permeance of all of our assembly should be so tight anyway, who cares? As soon as your permeance of your assembly gets below 1, the rate of water vapor diffusion is so slow as to be neglected. So whether it's 0.6 or 0.2, who cares? I have no concrete evidence that it makes a damn bit of difference. I don't even have a suggestion of any evidence that it makes a damn bit of difference.
Did you do a blower
However,
test?
there's some marketing people that are really rich now. I'm sorry, Mark, go ahead.
Did you do a blower test on your house?
Not yet. The range of blower door tests we've gotten from our clients, like I'm upstairs right now because I actually have drywall here. The range of blower door tests that we've gotten back from our clients range from 0.3 to 1.1 ACH 50, which is, a passive house is 0.6, and a quarter of our clients beat that, most of them by accident. And when we find a leakage, you go around with the IR camera and a smoke stick or a theatrical smoke machine or whatever. It's always the same things. Dryer vents, vent stacks, chimneys, range hoods, basement doors, and around the windows and between the concrete and the pressure treated sill. It's always the same thing.
Paul, did I hear you say that you do structural engineering for builders and so on, that you are not supplying the SIPs for?
No, we only do We only do those services when we are supplying the panels. We do it as an accessory to supplying the panels. I don't know if you can, let's see. That's my boiler flue and waste vent stack in my attic. They're up near the ridge, so there's less stuff to slide down the roof and hit them.
Mm-hmm.
Carol doesn't have to care, she doesn't have snow.
Got some bad floods and hurricanes, though.
You got to respect those, but you got to design for the environment you're in. Yeah, a 70-pound snow load doesn't really happen down your neighborhood.
Mind you, they do get snow in Houston, but it does leave like the next day or something.
I was going to say, 2 inches of snow is a lot.
Yeah.
When you're picky and slow and do your own plumbing work, everything winds up being nice and square and things. And my mom calls my utility room the engine room.
So you got radiant floor throughout?
Yes.
Yes.
That's the better view of the whole thing. The gable with the garage door in it is 20 feet wide, give you an idea of scale.
Cool.
The whole house is, the longest dimension of the house is 44 feet. And this is the only side with 2 stories.
Can you comment on the cost difference between building with SIPs and building with modules?
No.
With prefabricated modules? Oh my God. Double?
I'm sorry, I didn't hear you.
Compared to the normal modulars we see around here, we're half again or double. Although the energy performance is better by a factor of 8 or 10.
With the SIP?
Yeah. No, it depends what environment you're in. In Massachusetts, all buildings, modular or not, have to meet the same energy code. In most states, there's an energy code for houses and an energy code for modulars. And even though they both may be code compliant, the modulars are working to a much, much lower level. The threshold is much lower. Heat loss is much, much higher.
No, I'm not talking like a double wide module. Modular.
No, I'm talking about four boxes make a colonial.
Yeah, yeah.
Yeah, that's what I'm talking about. Because, and this is a conversation Gio and I had last year, I think, the regulations for those 4-box equals a colonial kind of modulars are the same as manufactured housing, single wides and double wides.
Well,
they are well below the IRC. They never tell you about that in the brochures.
But aren't this, modular manufacturers that build high performance modules?
There are a few.
Yeah.
Gio probably knows who they are better than I do, and I've come across a couple, but it's not at all universal.
What I agree with what you're saying, Paul. It's just that for the manufacturers that are doing a home, not a double wide or a trailer home, as some people call them, those homes are built to the higher standard than to that regular standard. So what they do is you're right. They do look at it as, oh, this is a modular home, so they go on a lesser standard. But if you go to a place like Vermont or even PBS.
Vermont is up there. I mean, there's the place up in Claremont is one of the companies I struggle with, because they're, having had clients that have investigated them and then asked for substantiation of their claims, it has not gone well.
Right. But the one that I'm really actually leaning towards is Vermont.
Yep.
PBS is the one I think you're talking about, and that's a little. They've got a bunch of stuff there. They've done a couple of homes. They've done a couple of passive homes, but I mean,
That's not their bread and butter for sure.
It's not their bread and butter for sure, and it definitely was on a one was a pro bono, and the other one was for someone who's paying. So I mean, it was on a higher scale, but it's like anything else. When you're going into these manufacturers, you don't rely on them to tell you what the code is. You're going in there, and you should you say, look, I want a well-insulated house, and we're telling you that if you go for an R30 in the walls and an R50 or 60 in the ceiling, you're doing okay. Okay, I think you're more than doing okay. I mean, we've
you have to be active in the process. There's no question.
Yeah, that's exactly it. So you don't really rely on them to say, oh yeah, it's the code. It's like, no, this is what I'm looking for. This is what I want, and they need to show it to you. They need to show you what kind of insulation are they using. How, and you need to take a look at how the assembly is put together, as Paul's shown you here. It sips, and then after that, how the windows are wrapped and how everything is flashed. And I don't know if we got to this in our discussion, but what I tell people, any of the classes, whether it's the prefab class or the home design build class, I tell them you need to put your money in 3 places. Okay, good insulation, good windows, and the third one that follows from the first 2 is a mechanical system. And the only way you're going to get your mechanical system really well, a good mechanical system, is, first of all, you're going to need someone who's an engineer, an HVAC engineer, who knows what he's talking about, who knows what he's doing. Never mind knows what he's talking about. Because if you've got good windows and you've got and you insulate your home, not just insulate it, but really seal it, okay? Now you've won the battle. Okay? I mean, and what you need to do is you need to really look at that. That's where you're gonna. I think you should be spending your money when you're saying, okay, here's our budget. It's okay. Well, let's insulate the home really well, number 1, and seal it. And number 2, let's get some windows that are worth it. Okay. And Paul made a good point about, there's no windows around that, they build to, what was it? A U point 0.1?
No, to break even in my climate, it was 0.07 or 0.08, something like that. It was better, the kind of windows that don't exist.
Right.
Or that none of us can afford.
Right. Okay. So, I mean, you really need to, and you need to kind of like do your research on that. I mean, you can, Paul put in double pane windows, and he made sure that, the windows facing south, there are ones that have e-coating and ones that don't. So there's a whole conversation there that you need to kind of wait the guys. Go ahead. Sorry.
To put numbers on it for everybody, right here we are at 7,500 degree days per year, and the design day heat loss of this house is 11,000 BTUs an hour. The smallest boiler they make is 50,000. So I'm roughly a fifth or a quarter of the heat consumption of the smallest boiler they make. And the house isn't that tiny. So this is where engaging somebody in a mechanical engineer is great. The main thing you need is a heating guy that isn't afraid of math and is good at critical thinking. And once you got that, if you get somebody that's good at critical thinking and a decent Boy Scout, you're going to be fine.
It's like anything else. You just got to shush him up.
Yeah, right. I just put this picture up, Gio, just to show you the levels of the obsession, but this is my ground loop that is buried in the same trench as my propane line. So my ERV doesn't have a defrost cycle. So an earth loop of water circulating through this tubing will then flow through a heat exchanger to somewhat warm the outdoor air before it gets to the ERV.
Okay.
So now the ERV never gets 10 below air.
Right.
It might get 30-degree air, but that's okay. That won't freeze anything.
Right.
And just for efficiency's sake, I figured, well, I got this big trench for the propane line anyway. What the hell? They got to put that 3 feet down so you never hit it with a shovel.
Right.
And I put that in too.
Paul, say that again. So there's water going through those?
Yeah, this tubing here that's in the bottom of the trench has got a small circulator on it. And of course, it's a ECM circulator, so it's like the little one is like 8 watts. It circulates water through this, through a water to air heat exchanger and back. So that the air that is passing through that heat exchanger comes from outside through that heat exchanger to my energy recovery ventilator. That coil of that heat exchanger will be 40-ish degrees, 45 degrees from the ground. Will warm 0-degree air up to 20-something or 30 before it gets to the heat exchanger core of the energy recovery ventilator. So I've gotten free BTUs, and my ventilation system, the heat exchanger of my ERV no longer needs a defrost cycle.
Why not just have the air come from a pipe that's buried from a similar length?
I can't see it and I can't clean it, and that's the air I'm breathing. The heat exchangers in my basement where I can take the panel off and I can see it and clean it and filters and all that kind of stuff. And the water that's in this loop is trapped there forever, so I don't care how nasty it is. And I made my own porch mounting brackets and I have them galvanized because I'm a nut.
Nice.
It was fantastic dropping these things off at the galvanizing shop. The galvanizing place in Connecticut does most of their work doing guardrails and those big overhead interstate signs.
Mm-hmm.
And then there's me in my little car. So lined up in the morning was me and 6 semis. And my dad and I spent a lot of time in the basement priming all the siding.
Both sides, right?
Pardon?
Both sides? Oh, wait, no, it's cedar. You don't have to do that. Okay.
No, I did do that. Actually, the siding and the trim all arrived naked because the pre-painting quality I've seen is just horrendous. Okay. So everything was primed, all 6 sides. Everything got one coat of color on all 6 sides. Then it went up on the house, and then the outside got another coat of color.
Yeah. Okay, good.
And by the time I have to mess with it, I should be dead. But I made drying racks in the basement and stuff.
Right.
So I hope that helps.
This was fantastic. Thank you for spending as long as you did. Really appreciate it. And I just wanted to get back to Ron's question. If you're going to compare, you got to compare apples to apples. SIPS gives you a good outside structure. It gives you, it's kind of like a threefer. Okay, it gives you insulation, it gives you structure, it gives you air tightness if you know what you're doing. And when you're comparing it to a modular, you're kind of comparing apples to oranges because a SIPS is a system you bring to the site, you put together, and then you get a builder to complete, like he said, like Paul said, the other 98% of it. Whereas with modular, and if the modular guys, if you can, if they're good guys and you push them, you can get a good portion of your building pretty much done. So that once it comes on site, they actually put everything together. They guarantee that it's waterproof, and so now you're kind of comparing apples to oranges. I mean, I think Paul's price there was $31 a square foot compared to a conventional, which was 27, and that's just for you're comparing to stick built and insulation. Okay.
Stick built insulation, rigid on the outside, and an air barrier.
Okay, there you go. So that's
no electrical, no nothing like that. So who knows
right.
how well the air barrier survives?
Right. So that's just, let's call it framing. Okay. So $27 a square foot, whereas using SIPs is $31. Okay. And they're there 2 weeks less. Okay. So if you want to take it from a carbon standpoint, that's a plus. If you want to take it from a standpoint of even money-wise, is as a builder, they don't have their guys there that longer. They can actually move their guys to the next job quicker. Okay. But that's okay. That's comparing to conventional. Now, if you want to look at a modular, you're looking at anywhere between 125 maybe to $175 a square foot. Okay, and that is kind of a big range. But I mean, it all depends on the size. It all depends on the design, and and a couple of and what you pick as finishes. That's why when you're going in and you're looking at these things, it's important to think of, first of all, you're looking at longevity. Is this thing going to last longer than I am? Number one. Number two, what type of insulation and how do they insulate it? How do they seal it? Because a lot of these things, when they're built so that they can go down a highway at 80, 90 miles an hour. That's like hurricane winds in some places. So they're pretty strong, and they're built in a controlled environment. All right, but again, you got to take a look at, structurally, yeah, they're good, but insulation-wise, how are they sealing them? What are they doing? And one of the exercises that I think we threw in at you on the second or third one, after the second or third assignment, was to find out who your prefabricators are in your area, whether using modular or panel or whatever, and go visit them. See, take a look at their shop, see what they do. And speak with them, and then come back and tell us what you've seen, and we talk about it. So you really need to compare apples to apples. There's no use saying, well, it's going to cost me more modular, but it's going to be less than SIP. Well, no, because SIPs is it's just like one aspect, one stage of the home, whereas modular, you've got 80, I'll say 80% of the home done. So I mean, you're not comparing apples to apples. So I mean, you really have to. That's not. It's what you're looking at as. What you're looking at as, okay, SIPs is a great insulating system, and if it's done correctly, it's bulletproof. Okay. What is it? First of all, take a look at your site. Can I get a modular down your site? Which was one of the discussions we've had, right? In this case, you're still going to need a crane, or at least some sort of forklift type truck to pick it up and move it around. Okay, so you got to see what you're getting for the environment that you're in.
Right.
So,
well, that brings up the question to Paul. Can a SIP be put up with a SIP house be put up with a? I have a location that I can't get a crane in. There's just too many trees, and we don't want to take the trees down. Can you do it with
a concrete truck in?
A what?
Can you get a concrete truck in?
yes and no.
I'm not sure.
Okay. Well, I mean, it's not usually a problem for us because you basically got to have a foundation. So we found that if you can get a concrete truck in and out, we're going to be fine.
Well, you get a concrete truck to the street, and I think some of them have very long hoses that you can do something.
But you can pump concrete a while, but we've got 140 feet worth of reach on some of our cranes as well. So we don't have to be parked right at the house. We do have to be able to reach there though. So I can't think of any jobs. There've been jobs that are tricky, but I can't think of any jobs where the site prevented us from getting our cranes in and out.
How far was it from the street to the house, did we say? Did you measure that?
It's probably about, could be 100 feet. Something like that.
It's kind of a stretch.
I mean, we've also done systems where we, knowing this from the beginning, designed it so that it can be basically raised by hand or by an all-terrain forklift.
There you go.
What we do is we don't use 8 by 24 panels. We make 4 by 16s and things that 2 guys can lift.
Right. Right.
That's another thing that is part of the customization that we do, is that if it's being assembled by us versus a rookie install crew, we often detail things a little differently because we know what we have. We own 4 cranes. So when we know we've got that in our pocket, we design it a bit of a different way. If we know it's a small-time builder, or we're building on an island in one of the lakes in the Adirondacks where everything's being brought in by canoe, we adjust the design of the panels to fit that site.
Right. Okay. Good. Thank you.
There you go. Cool. Well, Paul, thank you very much. You've been very generous with your time, and it was a fantastic talk. A lot of good questions.
Yeah, I hope it was interesting. I don't think anybody slept.
No.
Joseph's been very quiet, but he's been moving, so I don't think he was asleep.
Really appreciate it.
Joseph, you have no questions? You were kind of quiet. You had one, though. Anything else? No? Okay.
Thank you, Paul. That was great.
Thank
You're welcome.
you.
Anytime.
Oh, very good.
And if you have any other questions later, or think of something later, Gia knows how to find me.
Yeah. That's why you can ask him. Hey, Paul, I meant to ask you. You guys do lunch and learns?
Not really. Once in
Okay.
a blue moon. We kind of really suck at sales and marketing, so we live and die by word of mouth, and it keeps us busy enough.
Right.
But yeah, if there's a project in mind, we can work something out. Or if you got a stack of people, we can work something out. But
Yeah.
the lunch and learn thing is pretty rare, just because the ROI is not awesome.
Yeah, got it. No problem. Figured I'd ask. Sounds
Paul,
great.
you
Fair enough.
Go ahead.
Paul, you going to be at the Better Building by the BBD in Burlington?
Our company will be. I don't know if I will be. I'll bet you Allison, maybe me, and either Allison or I will be there. And if either one of us is there, we'll happily go over anything that you like. And we're about as big in a set of energy dorks as you're likely to find.
Hey, Mark, when is that?
Next month?
Yeah,
Cool.
I'll tell you exactly.
That is,
February 7th and 8th.
yeah,
Cool.
that's right.
I'm going to be in Vermont. I guess I'll go to that.
It's close.
I'll be there for the first day.
Cool. All right.
Well,
Thank
good
you,
luck,
gentlemen.
everyone.
Thanks again, Paul. And yeah. Anybody else? Any questions before Paul goes? No? We're all good? All right.
Thank you.
Good night,
All
Gene.
right.
Good night,
Well,
everybody.
good night, guys. We'll see you next week, next Thursday, okay? Next Thursday. All
Bye,
right.
everybody.
Bye-bye.
Yeah.
Good night, everyone. Thanks, Gio.
Have a good night. Thank you, Paul, very much. Thank you.
Thanks.
And I'm the last one standing.